Howdy. I am Calvin, and before I begin, I do need to give a little bit of context about what OpenHands is in the first place. So OpenHands is a model-agnostic, self-hostable, MIT-licensed coding agent. It's able to write code, it's able to execute shell commands, it's able to interact with the browser, it's deployable anywhere you want, it runs locally, it runs in the cloud, it's integrated with GitHub, with Slack, with Linear. We're working on Jira integrations and new integrations all the time. And this is a really exciting project to be working on, in part because the fact that it's open source, the fact that it can run almost anywhere, means we have companies that are trying to do some demos and do some trial runs with software development agents that may not be able to use existing offerings. They want to be able to control the entirety of the ecosystem. They want to be able to inspect the source code, make sure there's no funny business happening. It's also really convenient for us because it gives us an excellent platform for sort of pushing the boundary of what an agentic software development agent can do in the first place. We can very easily hack on the agent. We can put it into new situations. We can give it new tools. We can do all of these fun experiments with it. It's a really exciting place to be. So just a brief history. I suppose this code generation via language models really started kind of back in 2022, but we were in this space where we had very context-unaware code generation. By 2024, though, we're at the point where agents are able to perform atomic coding tasks. You can give them a ticket, something like adding a new endpoint and verifying that it works, and the agent, without much supervision, is able to perform every single step of that process. Look at the existing code, add new code, add tests, run tests, interact with the browser, verify every single step of this pipeline. And where we want to be in 2025 and where we've spent most of the year working is on parallel agents for large-scale work, starting to scale up beyond just a single agent and starting to work on modifications that have to impact and touch the entirety of the code base. To give a couple of examples of the kind of large-scale work that we're really interested in doing, we're looking at things like migrating a large existing code base from one library to another, possibly doing version updates. Maybe it's based on a particular library or implementation or even a programming language. Also doing code style standardization, type checking, making sure there's no awkward code smells or anything that exists inside your code base. Database schema migrations, both modifying the database and everything downstream that might depend on that particular schema. And our ultimate long-term goal is to be able to translate between different languages relatively automatically. This is sort of the final step that will unlock the ability to modernize a huge amount of legacy software that's propping up a tremendous number of industries across the country and across the world. A lot of these examples have come from customers that we've been working with, people in the open source community, and of course we've been experimenting with this type of workflow on OpenHands itself. One thing that we were doing recently was making sure that all of our code base written in Python is nice and strongly typed, and so I'm going to be using that as sort of like a running example as we go through the remainder of this presentation. So there are some natural difficulties that we encountered and that you might encounter if you're trying to use coding agents to solve these sorts of large-scale tasks. The first is that agents have a pretty limited context window. This context window is always getting bigger, of course, but performance doesn't usually scale with the number of tokens inside the context window the way you want it to. And it doesn't take much of a code base to get to the point where there's just no room for the agent to actually maintain its own history, state, execute tools, things along those lines. The next issue that we really ran into is that agents, and maybe this is model specific, can be pretty lazy. They stop when they think they're done, not when they're actually done. And of course, defining done can be a little bit tricky in some situations. But it does mean that you need a lot of human manual intervention to make sure that the agents are staying on task and that they've actually done the thing that they said they were going to do in the first place. The last difficulty that we've had is that when you have long tasks with lots of steps, even if an agent is correct 99% of the time, when you're doing 500 steps, 1,000 steps, all these different very minor edits, it doesn't take long for this error rate to start to creep up to something that becomes just unacceptable. But there are more difficulties than just the agentic side of things. The human side of things also comes into play here. It's pretty difficult, at least we found, for your average software engineer to be able to take a very large scale task and decompose it in a way that makes sense. If you are trying to run parallel agents, that constant context switching of having to constantly monitor and babysit these different agents and switching back and forth can add a huge amount of mental strain. And lastly, for some of these very large-scale code migration style tasks that we're interested in doing, you have a very ambiguous definition of done for the intermediate steps. For example, if I'm translating a library from Go to Rust, or doing a big version update that fundamentally changes the semantics of the language or the module that you're using in the first place, you may not be able to actually execute the code in the intermediate steps and use those unit tests as like a sort of like a good checkpoint that you're proceeding in the right direction. So why is now a good time for us to start to tackle these issues? Well, language models are constantly getting better. They are better at reasoning. Inference is getting cheaper. It is getting faster. This makes it much more cost-effective to spin up multiple agents, even if some of that work might be speculative, for example. But the ecosystem around software development agents is also changing. At OpenHands, we have these cloud-based sandbox agents that other providers have as well, which means that these agents don't have to worry about stepping on each other's toes. We've started to experiment with multi-agent interfaces to help reduce that burden and that sort of mental strain of trying to manage multiple contexts simultaneously. And of course, after having spent a couple of years working with these software development agents and trying to push them into places where maybe they shouldn't be in the first place, we have a much better understanding of the agent's strengths and weaknesses, the types of tasks that they're good at, and the types of tasks that they're bad at, and how to prompt them to know the difference between the two. And if you take anything away from this talk, maybe it's this. This is key. Agents are usually going to be part of the solution when it comes to these migrations, but they don't have to be the whole solution. And in fact, you're leaving a lot on the table if you consider agents to be the entirety of the solution in the first place. So at OpenHands, we also have sort of a very particular perspective on agentic workflows. I think whenever they first came out, 2022, 2023, 2024, everybody was possibly scared, worried that we were going to be replacing software engineers. But our sort of fundamental thesis is that we still need a human in the loop. So the average workflow looks a little bit something like this. A human sits there and prompts the agent does some amount of work, brings that work back in so the human can check it, and then possibly provide a new prompt to repeat this process. We go from there. If we want to start to consider this very parallel agentic workflow, it might look a little bit something like this. We have a human who has to sit there, take their original prompt, their original idea, break it down into some tasks that they can then give to the agents. The agents can then, hopefully, in theory, work in parallel and all produce some amount of work, some unit of work. And then the human that sits at the end of the pipeline has to come through here and combine all of these outputs together into some sort of cohesive product. So this may be a little bit egotistical, but at least at OpenHands, we're pretty confident that this middle part of the pipeline is not the bottleneck of this issue. Agents are good, and they are getting better as we continue to learn more about them, as models continue to get better. And so I'm not really concerned about what the agents are doing inside this particular breakdown. What we really find as the issue, the really limiting factor, the bottleneck here, is what happens at the very beginning of this process and what happens at the very end of this process. At the very beginning of the process, a human has to sit here and come up with this breakdown of tasks that it can hand off to the agents. But it turns out it's very difficult to come up with a breakdown that is both good for humans and good for agents. And I'll talk more about this in a little bit. The other thing that is really tricky is the human has to take all of these disparate changes and try and bring them together into a single representation. That context management and the verification of each of these individual changes is a huge bottleneck. So these two points I've made in red are what we're going to be spending the rest of the talk talking about. We'll start with just some of the tricks of the trade that we've learned trying to push agents into this context, mostly to solve this context management and verification bottleneck. So unfortunately, it also turns out that your average software engineer already has to worry about managing multiple different contexts, trying to consider multiple changes simultaneously, and we've developed tools for dealing with this. And that tool is, of course, version control. And so core to our workflow at OpenHands is version control. This allows us to give agents very distinct workspaces so that an agent is not necessarily running on your local computer, modifying the same files that another agent is. Instead, oftentimes they are in a separate work tree or containerized somehow so that they don't have to worry about stepping on each other's toes. And at least at OpenHands, our agents are able to commit their work and spin up PRs as they think they've completed these tasks. And this is really great because this is an opportunity for human intervention, which again, we believe is a necessary part of this process. This gives the humans a chance to review the quality of the code like they would do if the code was not written by an agent but written by a human, to provide feedback so that the agent can keep on working. You don't always brand every single PR with a looks good to me. Oftentimes there is some iteration to actually get to a final solution. And at least at OpenHands, one of our primary ways of communicating with the agent is by leaving comments on GitHub issues and GitHub PRs. And it's a very fun workflow. And then lastly, this gives the human a chance to actually merge the work so that the next batch of agents can keep on making progress. Maybe they have to merge some of these changes, maybe they have to merge all of these changes, but it at least gives a chance for the human to sit in the loop and have some control and some verification. Another trick, and this one is perhaps a little bit more difficult to explain and also difficult to set up, is scaffolding. As these agents are making their changes, it's entirely possible that maybe you're translating a very large existing code base from Python 2 to Python 3. You might not be able to, in the intermediate steps, actually execute the entirety of that code base. Your unit tests might break, your integration tests might break. So what you can do is set up a scaffold that, using something like an environment variable or a switch, lets you live pre and post migration. As an example, maybe you're writing a React app and you want to have two different state management systems. You have your old state management system and the state management system that you're trying to translate to. This way, you can get agents working on tasks to basically achieve feature parity between your old implementation and your new implementation. And then when you're done and the migration has been complete, you can just rip out the scaffold and you're left with a post-migrated code base, which is excellent. Of course, this is very tedious, but it turns out this is the kind of work that agents are particularly good at doing. And so it's very likely that an agent is going to be able to handle this type of process for you. So already our sort of simplified parallel agent workflow that has a human on both ends of the loop might start to look a little bit different. There's probably going to be some collaboration with a human and an agent at the very beginning of this pipeline to ensure that the code base is in a space that is amenable to these types of changes in the first place. And lastly, for the tricks of the trade, is context sharing. You're going to have agents that are exploring the entirety of this different code base. They're going to learn things as they go, and it's important that they're able to actually share those learnings with each other. There's a bunch of different strategies you can try based on the type of code base that you're exploring and your own personal preferences. You can share everything. Which is great because agents will always have the context of every other agent that's running the system. That's a good thing. It's also a bad thing. You're polluting the context window and you're making it so that agents are going to have a harder time focusing on what actually matters. You can have a human in the loop who is trying to share these findings, which is excellent, but you're going to get high quality learnings, but you're not necessarily going to get a very happy software engineer, because they have to be very carefully monitoring these agents for relevant discoveries and then populating it by pasting it into new prompts and things like that. One of the ways that we recommend is just by using a shared file of learnings. Many of these existing coding agents, Cursor, Copilot, do something very, very similar, where they will sort of examine their own trajectories, find out information that they learned about the code base that might be useful in the future, and write it out to a file. This is pretty easy to propagate, but we've also found that sometimes agents don't learn very useful things. It's very easy for them to sort of focus on the wrong way to run tests, and when in reality they should be focusing on the system architecture, something along those lines. And lastly, if you want to get really experimental, you could try something like message passing. If you have multiple agents running in parallel, why can't they communicate with each other in real time by sending each other messages? We've experimented with implementations of this. Sometimes it works, sometimes it's not. The trick that we've always run into is that agents have to know about the other agents. That's extra contexts, and it's extra room and decisions that the agents have to make. It's just giving them more opportunities to mess up. So this might work in some situations, but we've not found it to be particularly successful when migrating these large code bases. Now, for the rest of the talk, I want to focus on the other end of that particular pipeline. Instead of trying to deal with the context management and the verification bottleneck, I want to talk about breaking down tasks. How can we take a large existing code base and start to divvy it up so that we can actually have these agents work in parallel to try and perform this large-scale code work? So we have a very opinionated interpretation of what a good task is. A good task is one-ish shotable. And what I mean by that is that you should have a reasonable expectation that if you tell the agent to try and resolve this task, it will do so without human intervention. The challenge with having tasks that are slightly larger than this, that require human intervention in the meantime, is that if you're spinning up multiple agents in parallel, now all of a sudden the software engineer that is actually managing this particular migration has to sort of sit there and babysit and manage, and we're right back to this sort of context overload issue. Second, a good task should fit into a single PR. This is already sort of like a measurable unit of work for a software engineer. We should have a reasonable expectation that agents will adhere to the same standard. Third, tasks, if they are well designed, should be able to be executed in parallel. If you have tasks where multiple agents have to be modifying the same file at the same time, you're very likely going to run into deadlocks, and that's no fun to sort through later. And lastly, and this one is a little bit trickier to define, is that a good task is verifiable as complete or not as soon as the task is run. And I say this is a bit trickier to define because unfortunately, complete or not really depends on the kind of migration that you're doing in the first place. If all you're doing, like what we've been doing, is attempting to add strong type hints to your untyped Python library, then this is pretty straightforward because you can just call mypy after the agent is done, and it will tell you if there have been any errors or not. But if you have this very large like refactor where you're translating from one language to another, this verifiable as complete or not might require some work from the human to set up some sort of testing infrastructure that is actually using the unit tests of the old language to test the new implementation in the new language. Agents, again, are pretty helpful in actually making this work in the first place, but it is unfortunately very context specific. So if you're trying to migrate a very large code base, your natural inclination might be to just break the code base up into pieces and then start to work piece by piece. And you can break it up into as many pieces as you like at whatever granularity you like. The common ones that we see that people like to try are break it up by functions, break it up by classes, break it up by files. And I think that's very well intentioned, but it's probably a little bit too granular. So to give sort of like a sense of the kind of complexity that these code bases that we're considering actually have in the first place, I've generated this graph here. This graph, every single node represents a file in the OpenHands repository. And every time you see an edge from one node to another, that represents a dependency, where one file is importing code from another, either implicitly or explicitly, which annoyingly sometimes you can do in Python. This code base is not huge by any means, but it is relatively large. We've got 383 Python files, 62,000 lines of code. There are a couple of import cycles, unfortunately, that we have to worry about breaking. And we have over 5,000 commits from 400 plus different contributors. So there's no consistency in terms of the style. Again, OpenHands is an open source project. We love any contributions that we can get. Sometimes that means the code is not always of the highest quality or adhering to the highest standards. And I'd like to point out that this is just sort of like the dependency graph representation for the core agentic loop of OpenHands. It does not touch the testing infrastructure, which is another 30,000 lines of code, or a very extensive evaluation infrastructure where we actually test OpenHands across various different benchmarks, which is another 60 to 70,000 lines of code. So this code base very rapidly becomes unreasonably large. If you wanted to break it up based on files and apply an agent to every single one of those files, you would have to spin up 383 independent agents. And now all of a sudden you're in an issue where you have to order them very carefully. You can't just have them all work simultaneously, or they're going to start making breaking changes on parts of the code base that never actually get a chance to meet in the middle. So this may not be a reasonable approach, but it does give us a little bit of insight as to what a good approach looks like. And that is maybe something like this. So in this example, again, we are just trying to add some strong type checking to our Python implementation. So let's assume we have two files, foo and bar. Foo defines some function which is just totally untyped, and bar has an import of that function and then a wrapper around that particular function. And this is just to illustrate that the order in which the agent actually attempts to resolve these issues matters tremendously. If the agent decides to look at the first file first, to look at foo first, it will find an untyped function. MyPy is going to throw an exception, and it will go through and attempt to add whatever strong type hints it can actually provide in the first place. Hopefully the code is actually amenable to these types of hints. We'll assume that it is. By the time it gets to bar, there may be nothing for the agent to do in the first place. If foo is well typed, bar, this function, is already well typed, and the agent is done. But if, on the other hand, the agent decides to try and analyze bar.py first, it's going to find a typed function that is calling an untyped function, and the only fix that it can do in bar.py is to simply add a type ignore, which is the opposite of what we want. This is common in agents. They attempt to solve the problem, not necessarily by actually doing what you want, but by doing what is easiest to make that little green mark pass. So this tells us a lot about what a possible solution should look like. The first is that we have tasks, files, that should be unblocked after their dependencies are resolved, not necessarily before. We should not really attempt to try and resolve bar.py until we've resolved foo.py. And the second nice takeaway here is that extra context is often needed anyways. As you're typing bar.py, you need to know a little bit more about foo. Which leads to sort of the next iteration of our approach, which is to take that existing file structure that I showed you previously, the dependency graph, and start to group it up. Start to generate a simpler graph where each of these nodes represents a collection of files, and the edges are generated by collapsing the existing edges. Now, there's a number of different ways that you could try to do this grouping. You could group by file structure. You could group by code complexity. You can actually run some static analysis, compute cyclomatic complexity, and try and make it so that every single one of these tasks has, about the same difficulty. You could apply some graph theoretic algorithms and attempt to actually group all this up based on clicks to try and minimize the number of edges between these different nodes. Any of these strategies are probably going to get you a reasonable enough graph. But what we've discovered is that this sort of like task breakdown, if we have good graph structure, meaning there are not too many edges between the nodes, there are no cycles, so on and so forth, we oftentimes have very bad PR structure. And by bad PR structure, I mean something that is difficult for a human to review in the first place. If our sole goal, for example, is to start to group up these files so that we have no cycles, we can fairly effectively do so just by exploring the frontier of this dependency graph. Assuming it's acyclic, we can end up with a sort of a very long chain of individual nodes. But if you actually look at the files that are going to be contained in each of those nodes, they're going to be totally unrelated to each other because the grouping was not aware of the semantics of the code base, the structure of the code base. You'll have a random file from one module over here and a random file from one module over here, all in the same PR, and that just gets to be a nightmare for a human to actually review in the first place. We like context, we like consistency, we like with like. So, we have a nice little trick up our sleeve. We already have a software development agent that is capable of running tools, examining code bases. So why don't we just let the agent actually come up with this particular task breakdown? In theory, it should be able to examine the files, understand the structure, and get us something that doesn't have any cycles, that has all the nice properties that we actually care about. Well, unfortunately, the task quality outcome that we get from here really depends on the input code quality. And when we're talking about migrating legacy code bases, this is challenging because we run into all the same problems that a single agent has when trying to do these large-scale refactors. It has to understand the entirety of the context of the code base, which probably isn't even going to fit in the context window. And if we're talking large legacy code bases, at least the ones that I've looked at, testing is pretty scarce, documentation is pretty scarce. Sometimes they're in obscure languages that nobody actually works with anymore. It becomes very difficult to assess the quality of this output here. So instead, what we've been doing is combining all of the above effectively. We take our algorithms that are good at generating a close to correct, but maybe suboptimal sort of task dependency graph. Maybe it has some of the properties that we care about, but not all the properties. And combining that with various static analysis tools, things that let the agent very rapidly move around the code base, like language server protocols, as well as complexity analyses to understand sort of where the hotspots in the code base are, where the real complexity lies. And we found that pretty effectively, if you give an agent the tools to manipulate these task graphs, a bad task graph, some tools, and a prompt talking about what a good task graph is, that very reliably the agent is able to turn that bad task graph into a good task graph. And then from there, our workflow opens up. So what we do right now, this is our current approach, and I'm sure it's always going to continue to be modified, is we start off with a human, an agent, and a bunch of tools all collaborating together to start to decompose the task into some sort of task graph like this. This is a very iterative process because it oftentimes requires the human partially understand the code base. And this is where we have a lot of room for improvement and experimentation. The user experience here is very, very critical. You want to give the human the tools to understand the code base, to explain the code base to the agent, and to understand the quality of the task breakdowns in the first place. Oftentimes this requires extra metrics. Code complexity analysis is something that we'd like to do a lot of. And then from there, you can have agents tackle unblocked tasks and start to open up PRs. All they have to do is look for one of these nodes on these task graphs that has no incoming edges. If we've done our job correctly, as we design a task graph, it should be a directed acyclic graph, and this becomes very straightforward. The agents go off in parallel, they make their modifications, they open up a PR, and then the human works on reviewing that and unblocking future tasks by merging that PR, or if necessary, starting to give feedback to the agents. What's nice about this is that the user interface that the software engineer is working with is basically just version control. We like to use GitHub. Most software engineers are very familiar with GitHub. This is already a very familiar interface. It's not a big leap for them to have to learn an entirely new workflow in this case. And because the primary mechanism of interaction is GitHub, and agents are pretty decent at writing good PR descriptions, and if we've done our job and grouped the tasks well and have generated good tasks, we should have some hope that the human is able to reasonably parse, understand, and give a thumbs up or thumbs down on these PRs. And lastly, all we have to do is repeat steps 2 and 3 until there are no more tasks left to accomplish. You just keep on pulling down unblocked nodes. As the software engineer starts to merge these, new tasks become unblocked. And at some point, ideally, we will finish. There are, of course, some major ongoing challenges with this line of work. It's still early days, I believe. The first is that every large-scale code modification task is very different. You have to consider different verification conditions if you're doing a simple version update than if you're doing a complete module swap or something along those lines. You might have to do some early work with an agent before you even get to this kind of task decomposition to make sure that your testing strategy is very sound. Next ongoing challenge that we have is that some of the steps of this particular pipeline are pretty well benchmarked, and we have some understanding of how well the agents perform in these sort of isolated contexts, but we don't have very good end-to-end numbers for this kind of approach in general. It's very difficult for us to look at a PR that an agent has generated and say, yes, that's a good PR, no, that's a bad PR. It requires a lot of human annotation, it requires context and understanding of the original code base, as well as an understanding of what those changes are in the first place. And lastly, and I've talked about this a little bit already, is that validating intermediate steps can be really tricky depending on the kind of code base that you're working with. If you're doing a total rewrite from one language to another, you may not even have the ability to run the code base until you get to the very end. And so you have to get a little bit creative with coming up with intermediate verification checks that you can do to make sure that the agents are staying on task. That's all I have. Thank you so much. I'd love to take any questions, and I will be here for a while, and definitely tomorrow. If anybody wants to talk about OpenHands, I'd love to show a demo, but we'll do so later. Thank you.
So you talked about the developer going through the PRs and unblocking tasks. This is the perfect slide for that. So when they're unblocking, are you saying that that graph remains unchanged and that will unblock the agents, or should that graph be regenerated as they're unblocking by merging these PRs in?
That is a very excellent question. Our current hope and understanding is that the graph does not change. And the visualizations that we have are kind of fun. As it becomes unblocked, these nodes turn green, and the green slowly starts to creep into the center of the graph, and that's very satisfying. It's like a measure of progress the human can look at and be like, oh yes, we're progressing forward. But it's not hard to imagine situations where we might actually need to start to regenerate this graph. As new PRs come in, that's new context both for the agents and for the humans, and it's entirely possible that the task breakdown that we have becomes inadequate. Or maybe it's fair to say that it was always inadequate, but we only learned about its inadequacy by starting to proceed forward. What's that old quote? No plan survives first contact with the enemy, I suppose. So we have not run into situations where regeneration is absolutely necessary, but it's definitely something that we want to explore in the future.
You talked a little bit about sharing learnings between the agents. My mind actually almost immediately goes to some form of pub sub or similar semantic with an arbiter, even if there's an agent there. Is that something that you tried or have thought about? Do you have any thoughts on that?
Let's see, some sort of pub sub architecture with an arbiter.
It would be message passing, right? Mm-hmm. The agent would have to say, oh, I'm ready to go see if there's learnings I need to find out about. And it could decide if, A, it's relevant for itself, and the arbiter could also decide that for it as well. Just kind of shooting from the hip there.
Yeah, that's an interesting idea. I like this concept of an arbiter as sort of like a final check of, yes, this is actually useful information in the first place. I think determining whether or not that information is useful is a problem with all of those sort of information sharing strategies in the first place. And so that could be something that could be integrated even into the single shared file that gets passed around, for example, like the cursor rules.md type of file. There is another issue with the sort of pub sub message passing architecture, and that's that it is in real time. And so it's entirely possible that you have agents that are learning the same things, or they are taking two different approaches to solving the same problem, and you might end up in weird race conditions where agent A decides to solve the problem using module A, agent B decides to solve it using module B. They both say, ah yes, we've learned something, and now your information, because it's being communicated in real time, is sort of conflicting. But that's a difficult conflict to detect in the first place, unless you have something like an arbiter who can actually sort of analyze those learnings, not just in the context of the code base and the agent's task, but also in the context of all the other learnings.
The concepts that you've been talking about today have mainly focused on migrating a large code base. Could the same tools or agents and such structure be used to just work in a large code base? I think we've got a huge legacy code base that we're adding to regularly, but coding assistants have really struggled with that.
Excellent question. The answer is yes, but maybe no. To give a little bit more context, in all of those sort of like large-scale coding tasks that I presented there, they all had one feature in common, which was that the end goal is to have a program which is like close to semantically equivalent to the original program, but with some modifications probably made in many or all files. And I think this type of like task breakdown is very amenable to those situations, but it may not be appropriate for arbitrary work on a large code base. If you're adding a new feature, for example, or you are trying to fundamentally change what the code base is doing, you're trying to re-engineer the architecture, you might need a different strategy for actually doing this type of task breakdown and architecturing.
So one of the problems that I see with these large-scale tasks is to ensure code completeness, right? So I want to compare this strategy that you have presented versus the code modifiers, which use AST to pass down the code bases, and then to me that approach seems more scalable. It seems more unit testable. What are your thoughts on that? LLMs versus code modifiers augmented by LLMs?
That's an interesting question. We have not experimented much with agents that are using code modifying tools very directly, in part because agents really, really like to just call shell commands and to do very manual file editing. Even if you try to prompt them into a different direction, sometimes they're very, very stubborn and set in their ways. Claude 4.5, Sonnet, Opus, whatever, really loves sed. Try as you might, you can't get it to use the string edit replace tool. I do believe that is useful once we can actually figure out how to ensure that the agents are actually applying these existing code modification strategies. I think the standard software engineering literature calls this refactoring, applying tools to take this AST and transform it possibly on a very, very large scale. That is something that could definitely be used to help boost confidence that the agent is actually doing the right thing here. Are there any other questions? I'm going to be around for a little bit, so if something comes up, feel free to come find me and bother me. I see we're out of time. Thank you all.